Uh, Hello, everyone. Welcome to the GROOT seminar. Today we've got Matt Feller talking about Quasi-2-Segal sets, and I'll let you go.
Okay, thank you. And thank you to Sarah for organizing this. Yeah, so I'm going to talk about Quasi-2-Segal sets today. And to say what those are, so they're going to be certain kind of simplicial sets, which means that I should start by saying a little bit about what simplicial sets are. So I'm not going to carefully define simplicial sets. The main thing is just to have a picture in your head of a simplicial set as being built out of simplices. So the zero simplices are like points, one simplices are like arrows, two simplices are triangles, three simplices tetrahedra, and so on. And then the kind of other main ingredient here is that we're going to think of each of these simplices as having faces. So for example, a two simplex is going to have these three edges as living inside of it, which are its three faces. And so the you get each face by deleting the corresponding vertex. So for example, deleting 0 gives you the D0 edge. Deleting 2 gives you the D2 edge here. And D1 is what you get from deleting that. So there's these three edges or arrows, one simplices that are living inside of this two simplex as faces. And so a nice way to encode what a simplicial set is more formally is as a functor from this category delta here, which the delta here is the category of finite linearly ordered sets. And so basically what this amounts to, though, is that for every natural number n, we have a set of n simplices. So the when you have a simplicial set, well, we've already, I mean, the picture has already been kind of in drawing might already be suggesting this. You can sometimes view your simplicial set as being like a category where you have your zero simplices are your objects, your one simplices are your morphisms. But then what you need to happen is you need to be able to encode composition. And so in general, in a simplicial set, anytime you have a pair of arrows like this that meet at this point here, there doesn't have to be something filling this in. So there doesn't have to be kind of anything composing here. But if you have this, but suppose you say that actually every time I have something like this, then there is actually a unique two simplex filling this in. Well, then this kind of gives us a notion of composition for our morphisms. And then going up further, if you have a string of three simplices like this, or three one simplices like this, then there's the unique three simplex filling them in. And more generally, if you have a string of n one simplices, sort of like this, continuing on, and then saying that those uniquely extend to some n simplex, then this is giving you, so a simplicial set that satisfies this condition is what we might call a one-Segal set, or just a Segal set. And really, it's actually precisely a simplicial set that's behaving like a category. In fact, you can make that precise by anytime you have a category, you can take what's called its nerve, and that gives you a simplicial set that has this property. And anytime you had a simplicial set that has this property, then you can cook up the category that it is isomorphic to its nerve. So these simplicial sets that satisfy this kind of unique spine extension condition are exactly what, we can just conflate them with ordinary categories. So the idea of 2-Segal sets is, this is usually people don't call them 1-Segal sets, they just call them categories or maybe Segal sets. If they're, but the reason I have the 1 here is that what we're going to do is we're going to talk about 2-Segal sets. And we're going to see in a little bit why this, what this 2 is saying. The 1 here is emphasizing the fact that these spines are one-dimensional. They're built out of 1 simplices. So we're going to talk about in a second things built out of 2 simplices instead. And that's where the 2 is coming from. But the idea is going to be that we still want to kind of have a lot of this picture stay the same for talking about 2-Segal sets. We still want to talk about our objects, our 0 simplices as being like objects, our 1 simplices are, we're viewing them as morphisms, and then 2 simplices, we are thinking of them still as kind of composition, except now what we're doing is in a 2-Segal set, we're going to say that a 2 simplex is a choice of composition. And it doesn't have to exist, it doesn't have to be unique, it just, anytime you have a 2 simplex filling in, it's something we might view as a chosen composition. And so we're eliminating, though, this kind of unique spine extension condition. We're not saying that anytime you have these, a pair of 1 simplices like this, that there's a unique 2 simplex. There might be a 2 simplex, there might be many 2 simplices, there might be none filling them in. So, yeah. And so what structure do we still have, though, in a 2-Segal set? Well, we're still going to have some notion of associativity. That's going to be the idea, is that we don't have unique composition anymore, but there's some kind of associativity still. But the thing is that we can't quite use, so first guess for what a good notion of associativity would be this picture here, where anytime you had 3 arrows, then there should be a unique way to compose them. So maybe you would want to fill in this with a 3 simplex here. But the problem is that if you have uniqueness here, then actually you can get a unique composition out of it for just 2 arrows. So it's not quite, this is not quite what we want. That we don't want to just work with 3 arrows like this and then say that there's a unique 3 simplex. So the picture that of associativity that's going to work when we move to 2-Segal sets is something like this, where we have kind of F, G, and H here on the outside. And so one of these pictures is showing, well, for now, maybe let's think about just the ordinary category case where this is showing that F and G compose to GF, and then this composes to HGF. And this picture here on the left here is showing that we've composed G with F first and then with H, and then this should be the same thing as composing in the other order. That's kind of the picture here. And so one way of saying that these things give you the same thing is that that they're both living inside of the same 3 simplex. So there's a unique 3 simplex here, which these 2 faces are one of the pairs of faces, and then the other pair of faces is given by these other 2. So this picture here is still actually going to work just fine once even though we've gotten rid of unique composition in 2-Segal sets now. And the idea is that we are now saying something slightly different, which is that anytime you have F, G, and H like this, and then you can pick a way to compose, So this two simplex is now kind of a choice of composition here. And then from there, you pick a way to compose that with H. Then there's a unique 3 simplex extending that. And then when you look at the other two faces, that gives you a unique way of choosing in the other order. So it's the same kind of picture, but it's saying something slightly different. And basically, it's the closest thing to associativity that you could expect when you don't actually have unique composition. So this is the picture here, and what this actually. So let me go to. So like you could kind of do this more generally. Just anytime you have n arrows like this, the arrows themselves don't uniquely extend to some n simplex. So here I have a string of 5 arrows. The arrows don't extend uniquely to some 5 simplex, but once you've picked a way to compose them, this 2-dimensional picture here where we've picked, composing this with this, composing this with this, composing this with this. We've picked all these compositions here. Now this uniquely extends to some 5 simplex. And same idea for any kind of triangulation of an n+1 gon. And so this is the idea, is that we're, remember that the 1-Segal sets were simplicial sets that behaved like categories. Now the 2-Segal sets are a similar idea, except it's a multi-valued category, you might call it. The composition is not necessarily unique or even defined, but it's still associative in this certain way. And this associativity is encoded by this kind of unique extension of what you might call 2-dimensional spines. These pictures that I've been drawing here of 2 simplices glued together in a certain way. Okay, so yeah, let me give you an example, because this might seem like a very weird thing to talk about. So yeah, so the example I'll start actually by talking about something that is a category. So I'm just going to start by talking about 2-Cob. So this is an ordinary category where the objects are kind of disjoint unions of circles like this. And then, so here's an object with 3 circles. Here's an object with 2 circles. And the morphism between these objects is a cobordism. So it's this 2-dimensional manifold with the boundary is these disjoint unions of circles. And so then this is giving us a morphism from this disjoint union of 3 circles to this disjoint union of 2 circles. And then you had another this would be another morphism here. And then the way that you compose them is by gluing them together. And then, well, I should really be saying that these are diffeomorphism classes of cobordisms. And then once you glue them together, you kind of smooth them out so that it's still smooth in whatever way you want. And so this is the picture, is that you have your morphisms are given by these cobordisms, and you're just gluing them together to get another cobordism from this this object to this object. So this is, like I was saying, this is just an ordinary category. There's nothing 2-Segal-y here yet. But what you can do is you can modify this and say, I'm going to pick some natural number n. I'll just pick 1 because it works with the picture I've drawn, and say that I only want cobordisms now with Euler characteristic less than or equal to whatever number I've picked. So I'm picking 1 here. So then these two morphisms that I've drawn in blue are fine. This one's got Euler characteristic 0. This one has Euler characteristic 1. But then if we tried to compose these two, then there's going to be another hole showing up. So this would be Euler characteristic 2. So it wouldn't be in this 2 cob less than or equal to 1 anymore. So now this is not a category anymore because sometimes we can't compose morphisms. But it will be, so this without the less than or equal to 1 here, it was an ordinary category. It had associativity, like it doesn't matter what order you glue things together in. That same argument is going to work to show that it's got the right associativity you need to be 2-Segal. So even though composition isn't always defined, it's still associative in the way that we want for it to be 2-Segal. Are there any questions about this example? Okay. So that's kind of a fun one because you can draw pictures. This next one is a really important. In some ways, it's a central example of this 2-Segal theory, which is the S-dot construction. And so I'm going to talk about so in general, you can put very fancy things into the S-dot construction, but I'm going to stick with just the ordinary category of abelian groups because we're going to see that something interesting happens even with that. So this S-dot of abelian groups is going to, well, I didn't draw there's going to be just a unique 0 simplex. It's just kind of this 0 diagram. So in general, these, do you have a question?
Hi, yeah, I'm a little confused. So can you go back to the previous slide?
Okay. Do you want me to redraw my pictures?
No.
Okay.
I mean, I was a little confused because when you spoke about the 2-Segal set, you said that when we talk about associativity, we make a choice of what way we want to go about things. But in this example, there was no.
Yeah, that's
you just glue things together and you don't.
Yeah.
Or are you making a choice when? I mean, I don't know. I'm a little confused.
That's a good question, and I meant to actually point that out. That in this example, because we kind of started with something that was a category where you have unique composition, and then all we did was say sometimes you can't compose certain morphisms. We still had uniqueness from the fact that it was sort of living inside of a category in the first place. So we aren't really, there isn't any ambiguity in this example. It turns out that the picture is that sometimes you don't have composition of arrows like this, but when you do, in this example, it turns out to be unique. There's no ambiguity. So this example doesn't actually capture the full kind of like things, all the things that can happen with 2-Segal stuff. In fact, the next this S-dot, once I unpack it a little bit, you'll see that this has the other thing going on, which is that you actually always have composition in a certain sense, but then it's not going to be unique most of the time here. So,
okay.
Yeah.
Okay, thanks.
Thank you. So we have so the 1 simplex in this is going to be a diagram that looks like this. So with injective homomorphism on all of the, well, so in general in these pictures, all the horizontal arrows are injective and the vertical arrows are surjective. And we want all these squares additionally to be pushouts and pullbacks. So let me just kind of unpack what this is saying. So really, let's think about first just what the data of a one simplex is. So it's this certain diagram of abelian groups, but these arrows to and from 0 aren't really telling us anything. There's always a unique morphism to and from 0 like this. So all the data really is just a choice of abelian group. So the one simplices here are abelian groups. So we kind of have our, the things that are morphisms in this example are abelian groups. And then our morphisms are what we want to kind of have some kind of notion of composition of now. And let's figure out what that is. So a two simplex here is going to be some kind of choice of composition of morphisms, but so it's like some kind of choice of composition of abelian groups. So what is that here? So I didn't actually tell you how these one simplices are living inside of the two simplices as faces. So the way that you do that is that the so this is the D0 face, and how we get that is by saying, well, for 0, I'm gonna just eliminate all of the parts that have 0 in the index somewhere. So this is really A00, A10, A20, so all that goes away, and that gives me the 0 face of this two simplex. So that's but in the picture of a two simplex that we're getting rid of the 0 vertex. So over here we have this abelian group A21. And then similarly, the D2 face is going to get rid of everything that has a 2 in the index here. So this is really A22 down here. And so that leaves us with this part of the diagram. And so really this is just A10 here. And then it's a little bit harder to draw the when you get the one face here, we eliminate this part. So it's really this part of the diagram that we're left with. And so that's A20 here. So this is, this kind of diagram is telling us that A20 here is a choice of composition for these other two abelian groups, A10 and A21. But what is this really saying? So what this is really saying is actually, so first of all, notice that there's, actually, let me not use this color. Notice that there's kind of most of this diagram here, we can just kind of view it as a sequence here. And this condition that the squares here are pushouts / pullbacks is actually amounting to saying, so this being a pushout / pullback here is actually telling us that this is a short exact sequence here of abelian groups. And so in other words, we're seeing that the notion of kind of non-unique composition here is given by group extension. It's telling us that these two, given A10 and A21 here, these two abelian groups, a choice of group extension is kind of what we're viewing as our notion of composition, which is not in general unique. But like I was saying before, it does always happen to exist. So this is kind of the opposite of the example we just saw before, where it turns out that composition does always exist here. It's just usually not unique. So so yeah, so now the last thing to kind of discuss about this is why is this 2-Segal? So we just saw that composition, what's kind of the idea of composition here, and we just saw it's not unique. So it's definitely not going to be 1-Segal. This is not going to give us something that behaves like a category. But we want to see why it is 2-Segal. So I want to see why when you have, so remember that part of the condition was that anytime you had a pair of 2 simplices glued together like this, that they uniquely extend to some 3 simplex, which I'll try to draw. And so what is, let me kind of say or try to unpack what this information is in this context. So what it's going to amount to is kind of seeing what are the what's the union of this face and this face living inside of a 3 simplex. So here's a 3 simplex, and here's the D2 face or the D0 face of this 3 simplex. Remember, that was just deleting all the stuff that mentions 0 in the index. And then we're also, the D2 face is deleting everything that has 2 mentioned. So it's deleting this kind of L here. So we still actually have this arrow here. We have this arrow here in the picture. So what this is saying is that a pair of 2 simplices glued together like this looks like almost like a 3 simplex diagram, except we're missing this information here. We're missing this abelian group. So how can we recover this? We want to say that this pair of 2 simplices, which is this information of this diagram, except for this, we want to say that this uniquely extends to some 3 simplex. So we want to uniquely recover this whole diagram here. And so to get that, well, we remember that we want everything to end up being a push out / pullback. And so we can take the pullback of this this here. And so we take the pullback, and then since we have this map here and map going here, we get an induced map here. And then you can check that all the squares are pushouts and pullbacks, and all the maps are actually injective going horizontally and surjective going vertically, and everything that satisfied is supposed to be satisfied. So so that's how we recover that. But then if you're paying close attention, you'll notice that this is not quite what I was maybe implying was going to happen. Because if we're going to actually have a 2-Segal set, then it really needs to be truly unique when you have this kind of pair of 2 simplices. There has to be a truly unique 3 simplex that we can fill it out to. And that's not actually what's happening here. We have uniqueness, but only up to isomorphism. So this isn't really a 2-Segal set. It's a 2-Segal object, and it's really, you have to do something like change to your target here from sets to something like groupoids. And when you do that, you really, you have now, instead of a set of 3 simplices, you have a groupoid of 3 simplices where your objects are diagrams like this, and your morphisms are isomorphisms of diagrams like this. And when you do that, then you have the right kind of uniqueness that you need for it to satisfy the 2-Segal condition. But without doing something like that, it's not truly a 2-Segal object. So this is kind of what I was alluding to a little earlier, where I said that I was going to stick with putting in abelian groups here because we see that something interesting happens even in that most simple case. We didn't put in anything fancy here. We didn't put in any like infinity category, homotopy, anything. It's just the ordinary category of abelian groups. And somehow there still was this like this kind of looseness that we needed. We needed this up to isomorphism, or viewed a certain way, this up to homotopy thing to actually get something 2-Segal. And so this is actually this is kind of a general thing. Is that actually many examples of 2-Segal objects are not strictly 2-Segal sets, like I started talking about. They're really this up to homotopy thing. So let me say a little bit more about this, because this is the the question in the chat was just go back. Yeah, the zero simplex. There's just a unique kind of zero. Just the zero diagram here was the zero simplex. So there's kind of just a dummy zero simplex in this case. So when we so this so we had to kind of move to this up to homotopy version of things. And so when you do that, you can change your target to groupoids, but you can go even further and change it to, well, you can call them spaces, but really we'll see later that you can use simplicial sets and call them spaces anyway. So that's secretly, I'm not going to go into much detail about Segal spaces and things, but what a Segal space is what you call a simplicial space, and that's when you've changed your target here to simplicial sets. And we're going to see, I'll talk about it a little later, how you can actually view simplicial sets as being like spaces, like topological spaces. And so this is, so this is one approach to kind of getting up to homotopy versions of things, is that the corresponding notion for just ordinary categories, when you kind of move to up to homotopy, be Segal spaces. And so the same idea holds for 2-Segal sets. Really, most of the literature about 2-Segal things has actually been about 2-Segal spaces, for the reason I was just saying. A lot of the examples, even in more basic cases, turn out to have some kind of up to homotopy thing going on, where you don't really have a discrete 2-Segal set, you have a 2-Segal space instead. And so these 2-Segal spaces were introduced by Digorov and Kapranov, and also by Galvez, Koch, and Tonks independently about 10 years ago now. And this has been kind of the approach is to work with these simplicial spaces that satisfy this 2-Segal condition up to homotopy. But the thing is that, so as we saw last week, there has been work done with Segal spaces as well. It's kind of like this up to homotopy version of categories. But thanks to Joyal and Lurie, there's been a lot more development using this other version of like up to homotopy categories, which are called quasi-categories, or if you're Lurie, infinity categories. And it's a different idea where you don't change your target, but you weaken your condition. So instead of kind of doing what we just did, where we said we're going to change our target to groupoids or simplicial sets or something, we stick with a simplicial set and we just weaken what the condition is. So I'm going to say a little bit more about what exactly the definition of a quasi-category is, what this condition is. But this is the was my goal, was to do this same idea for 2-Segal stuff. So to have a version of, come up with a notion of quasi-2-Segal set, which is kind of the, staying in the world of simplicial sets and just satisfying this 2-Segal condition up to some weak notion. So, but I'm going to circle back and explain more in more detail what these things are. But this was the motivating idea, and part of the motivation is that a main example should be the kind of thing that I was just saying, where you have you kind of do the naive thing with this S-dot construction and just stay with sets. You don't change to groupoids or anything. You just actually define the S-dot construction the way you might naively do it, and just don't worry about groupoids or anything. Just talk about the set of diagrams like I was drawing. Yeah, and so this is what I was able to do, is to come up with a good notion of these quasi-2-Segal sets and show that they have a lot of the nice stuff that happens with quasi-categories actually does also happen with quasi-2-Segal sets. And in particular, there's a corresponding model structure. So I'm not going to get much into model structures at all today. If you don't know what a model structure is, the idea is just to kind of give a category a certain homotopy theory, like an abstract notion of homotopy theory to your category. And it kind of makes, if you have an associated model structure like this, then it sort of means that you have a more robust like homotopical object in a certain sense. That's maybe all I'll say about it. And then I'll also, I mean, the reason I'm mentioning it here is that this was a big part of the project for me, turned out to be kind of understanding what model structures are possible on the category of simplicial sets. It's a little bit, it turns out like it turns out to be a little tricky to define a model structure for these quasi-2-Segal set things, because it kind of is going in the wrong direction from what you might want to do in general. So, but yeah, I'm not going to go into much detail. So let me, are there any questions so far before I kind of circle back, and I'm going to kind of go into more detail, but what are these quasi-categories and what are quasi-2-Segal sets? Okay, so
sorry, can I? Yeah, no, just to recap. So in point 1, we were changing our simplicial sets to groupoids or spaces, and what condition were we not weakening? We weren't.
So it's yeah. So this is.
We were demanding a unique.
So the idea is that in this kind of world, so maybe it'll help if I do something like this. So in so when we haven't moved to kind of change the target here to groupoids or simplicial sets or anything, then we have something like this where we have a map that sends two simplices to kind of it sends a two simplex to kind of the it's a D2 face here and it's D0 face here. So it's sending it, it's sort of like if you have F and G composing to H here, then this is sending it to F comma G. And then there's like, they agree on their, that point there. And so this map has to be, when you have a simplicial set, and it's going to satisfy this uniqueness condition. This is telling you that this is actually a bijection of sets. And so the idea here is that once you've changed your target, now, so maybe this is simplicial sets or topological spaces or groupoids or something. Now we just want this to be a weak equivalence in whatever sense we're asking for. So to say exactly what that means with simplicial sets, it's a little bit tricky, but maybe think about topological spaces and instead. And so what we're asking for is that this is a so I guess in a sense we're still weakening the condition as well here, but it's really like it's where you're weakening it is the distinction. So we're like doing everything in the target here, but it's still kind of like the same condition in a way. Whereas that doesn't happen at all here, because this this map is now down here. You can draw the same map, and this is not going to be a bijection. They're still set. It's still a set map, and then this is not a bijection at all. And then somehow the which I'll talk about more in a minute. The kind of there's still some kind of uniqueness up to homotopy, but that's going to be witnessed by higher simplices. But that'll make more sense in a minute. So let's see. Okay, I'm gonna try to do this relatively quickly, and just kind of give a taste of how we can use simplicial sets to model topological spaces, because it's sort of the reason why any of this up to homotopy stuff actually happens in simplicial sets. And so if you have a topological space Y, you can get this simplicial set called sing of Y, which is a singular simplicial set of Y, where the n simplices, so this is the set of n simplices of this sing Y, that's going to be the set of continuous maps from, so this is my notation for the topological n simplex to our topological space Y. So the kind of picture here, let's see, when n equals 0, that's just giving you the set of points of Y. When n equals 1, it's giving you the set of paths in Y. And then when n equals 2, it's giving you kind of a set of sort of triangles like this in Y, and so on. And so so this gives us a way to to move a topological space over to the world of simplicial sets. And I want to kind of show you one of the, or like kind of what ends up being sort of the defining characteristic of sing Y here, which is that it has what are called horn extensions. So I'm going to just do this to demonstrate. Okay, so first I need to say what these things are. So remember that delta 2 here was the just the 2 simplex here. And so this notation here, this lambda 0, 2, this is a horn living inside of delta 2. And what this is saying is that we're taking the union of all of the faces of this except for the 0th face. So the 0th face here is this edge where we delete 0, so we have 1 to 2 here. So the union of all the other faces is the 0, 1, so the 2 edge, and the 0, 2, which is the 1 edge. So, so this is what a horn here looks like. This is the 0, 2 horn. And so what this is in Sing Y, it's a choice of one simplex and another choice of one simplex, which agree on this edge here. So what that looks like in Sing Y is it's some path and some other path, which both agree here. And what we want to do is we want to come up with a way to extend this to a 2 simplex here. So we want to extend this to some map from delta 2 to Y. And the way that we do that is actually just by kind of defining a map from delta 2 down to, and I'll kind of so this is sort of this is just a one simplex, or a topological one simplex glued to another topological one simplex like this. And basically this map here, so this is delta 2, you can kind of just push everything kind of projected this direction here. It kind of gives you a way to collapse delta 2 back onto just this pair of edges here. That gives you this map here. And so what that gives you is a way to, so this horn here was really a map from this push out here to Y. And so you can extend it to the 2 simplex by kind of precomposing with this sort of map here. And so the moral of the story here is that this Sing Y, you have some topological space and you take this simplicial set associated with it, it has these horn extensions. And so I've done it for 0, 2 here, but you can do it for any choice of I and N here. And so a simplicial set that satisfies this condition of having horn extensions like this is called a Kahn complex. And so we think of a Kahn complex as being a simplicial set that kind of behaves like a topological space for this reason. So this is kind of how we move from topological spaces to simplicial sets. We think we think of the simplicial sets which have this property that this horn lifting property. The Kahn complexes, we think of these as being like spaces. And so the idea of a quasi-category is to kind of have a similar looking condition which also sort of captures what we saw earlier, where we were talking about ordinary categories. So let me kind of just show you the definition and then explain more. So a quasi-category it looks almost the same as the definition for a concomplex, except we are only considering inner horns. So an inner horn is a horn where this index I is strictly between 0 and n. So that means that we don't have extensions of things like this anymore. So remember, this was lambda 0, 2. So when you have this in a quasi-category, so a map from this to X, there isn't necessarily an extension. But what we do have is lambda 1, 2. So this is the lowest level, or n equals 2. This is the only example of an inner horn. Anytime you have this, which is just kind of a pair of morphisms like this, then there does exist a filler here. So this is capturing what we were saying before about we want to have notion of composition here. Maybe I don't know, maybe I didn't say that before even, but that's the idea, is that in a quasi-category we do have composition of arrows. And the thing is that this composition is not necessarily unique still, but what we do have is that it's unique up to some notion of homotopy. So somehow the higher, for n bigger than 2, the simplicity, n simplices will sort of witness that any 2 different choices of composition here will actually be homotopic. And so maybe I won't dwell on this, but you could, quasi-categories are kind of a model of infinity 1 categories, and you could correspondingly say that concomplexes are actually infinity 0 categories or infinity groupoids, because they turn out to be exactly these infinity 1 categories where every one morphism is invertible. But the only reason I'm mentioning this is because is to say that remember that we were thinking of a 2-Segal set as being like a multi-valued category. So one way to kind of view what a quasi-2-Segal set is that it's going to be an infinity 1 multi-valued category. That's kind of that's all that I wanted to say here. So yeah, so let me give you the definition of quasi-2-Segal set. So the idea is to do almost the same thing as the quasi-category, except we are going to be missing 2. So our horns now are missing 2 faces instead of 1. And the condition that sort of corresponds to being the inner condition is actually that these are not adjacent mod n+1. So they're not adjacent on like the n+1 gon. So what that means for the lowest level n equals 3 is that the 2 options you get are the 2 triangulations of the square here. So this would be lambda 1, 3, I think. And this would be lambda 0, 2. Those are the 2 things you get in the lowest level. And so this this turns out to work out in a lot of the nice things that happen with quasi-categories actually turn out to happen with these quasi-2-Segal sets as well. So let me run through some of those properties. So this is kind of what I was getting at before. Actually, a way to characterize quasi-categories is that they're the simplicial sets where for every pair of morphisms or composable pair like this, then you actually have a simplicial set of all the different choices of fillers here. And this simplicial set turns out to be a Kahn complex, which is homotopy equivalent to a point. And so it's really saying that so in other words, a way of characterizing quasi-categories is that they are simplicial sets which have a notion of composition that's unique, up to homotopy in this precise sense. So another nice feature is that that there's an associated model structure, the Joyal model structure, and in fact, you kind of get this model structure by sort of starting with. So you can just it's what you get when you declare that you want your spine extensions to be weak equivalences, and then there also turns out to be an equivalence of model structures with a model structure for complete Segal spaces. And so all these features have analogs for Quasi-2-Segal sets. So a way of characterizing Quasi-2-Segal sets turns out to be that having a contractible space of fillers for these two different triangulations of the square that I've been drawing. And then also, like I was saying before, there's a model structure, and I didn't say this part before, but you can get this model structure just by starting with the two-dimensional spines. So those like extensions of different triangulations of the n+1 gon to an n simplex. If you just declare those to be weak equivalences, then the model structure you get, the fibrin objects turned out to be these Quasi-2-Segal sets. And this model structure turns out to be equivalent to a model structure for complete 2-Segal spaces, although I should point out that you have to be careful about what you mean by completeness of 2-Segal spaces here. There's different characterizations of completeness for just Segal spaces. There's kind of the original definition, but then there's also other characterizations of it that the equivalence of them kind of depends probably on the Segal condition. So the equivalence you get here, you have to pick one of those different characterizations in order to get this, to get the right notion of completeness that'll actually give you this equivalence. But yeah. And so then the last thing that I wanted to mention about these, because it relates back to the talk from last week, is that there's a characterization of 2-Segal. Well, so these Quasi-2-Segal sets turn out to have a characterization in terms of this twisted arrow construction. So if you were here last week, then we saw this twisted arrow construction, and it turns out that a way of characterizing Quasi-2-Segal sets is that a simplicial set is Quasi-2-Segal precisely if this twisted arrow simplicial set is a quasi-category. So this doesn't come out of nowhere. This is a kind of an analog of theorem for 2-Segal spaces, where another word for this twisted arrow thing is the edgewise subdivision. And there's this paper showing that simplicial space is 2-Segal if and only if its twisted arrow simplicial space is a Segal space. and this is what this is closely related to what talk was about last week. So yeah, and then here's the reference for that last paper. But yeah, that's all I have for today.
Perfect. Should we thank Matthew? And do you have any questions from the Zoom audience?
Yeah, so you mentioned that the Quasi-2-Segal condition was the appropriate one for the S-dot construction of the abelian groups. So do you know that if the S-dot construction for more general inputs is also Quasi-2-Segal?
Yeah, so so one of the let's see. So I'm on this page, and maybe I'll point out the two kind of papers that started this whole area are right here. Although this is one part of actually a preprint that involved got split into 6 papers here. So so Diggeroff and Kapranoff and Galvez-Cock-Tonks independently came up with this idea of 2-Segal spaces, although Galvez-Cock-Tonks called them decomposition spaces, but they end up being the same thing. Although technically they have different definitions, it just turns out that they end up being equivalent. And part of what I think helped people notice that they were the same is that they both use this, they both show that the S-dot construction gives you a way to get 2-Segal spaces. But so what you can do is that you have S-dot of something, maybe something really fancy, and you get, so I guess I should point out that you have to do something like maybe like a proto-exact infinity category. That's maybe the most general thing you could put in here. That will, if you use the kind of original Diggeroff-Kapranoff version, then that'll give you a 2-Segal space from this S-dot construction. So you can't actually put in, it turns out that a Waldhausen category is something that the S-dot construction would work on, but it doesn't actually give you a 2-Segal object. You have to, you are slightly limited to kind of something like an exact category and not more generally a Waldhausen category. But you can be a little bit fancier and do a proto-exact infinity category. But so the thing is that you can get this, you can use this S-dot construction from their paper to get a 2-Segal space. And what one of the things that I was able to show is that in general, if you have a 2-Segal space and you just kind of, you take the underlying simplicial set on just the 0 level of each, or the set of 0 simplices of each level of your simplicial space, then what you get is a quasi-2-Segal set. And so, for example, when you apply their construction to AB here, then you get this 2-Segal space. But then what you can do is you can just forget that you have a simplicial space and just take the underlying set of each of those simplicial sets, and you're left with this simplicial set, which is precisely the kind of just naive thing I was talking about before. And just, it's generally true that if you have a 2-Segal space and you kind of just take the 0 level of it, then you're left with a quasi-2-Segal set. And so that applies for AB here, but it also applies for any of the like fancier inputs.
Any other questions? In that case, should we thank Matt again? And I'll stop the recording now.